Welcome to the new section of this course, Advanced Use of STL Algorithms. Now let's move on to the video, Implementation using Trie. Let's start by implementing a trie class using STL algorithms. This is the entire code example. Here, we will implement our own prefix tree only made from STL data structures and algorithms. Let's understand the code. First, we will include all the headers from the STL parts we use and declare that we use the standard namespace by default. The entire program revolves around a trie for which we have to implement a class first. In our implementation, a trie is basically a recursive map of maps. Every trie node contains a map, which maps from an instance of the payload type T to the next trie node. The code for inserting new item sequences is simple. The user provides a begin-end iterator pair, and we loop through it recursively. If the user input sequence is 1, 2, 3, and then we look up 1 in the subtrie, and then look up 2 in the next subtrie in order to get the subtrie for 3. If any of those subtries did not exist before, they are implicitly added by the array index operator of map. We also define convenience functions, which enable the user to just provide a container of items which are then automatically queried for iterators. In order to allow the user to type my trie, insert A, B, C. We must help the compiler a bit to correctly deduce all the types from that line, so we add a function which overloads the insert interface with an initializer list parameter. We will also want to see what's in a trie, so we need a print function. In order to print, we can do a depth-first search through the trie. On the way from the root node down to the first leaf, we record all payload items we have seen already. This way we have a complete sequence together once we reach the leaf, which is trivially printable. We see that we reached a leaf when trie's empty is true. After the recursive print call, we pop off the last added payload item again. This recursive print function passes around a reference to a printable list of payload items, but the user should call it without any parameters. Therefore, we define a parameter-less print function, which constructs the helper list object. Now that we can construct and print tries, we may want to search for subtries. The idea is that if the trie contains sequences such as A, B, C and A, B, D, E, and we give it a sequence A, B for search, it would return us the subtrie that contains the C and D and E parts. If we find the subtrie, we return a const reference to it. The possibility exists that there is no such subtrie, in case the trie does not contain the sequence we were searching for. In such cases, we still need to return something. The optional is a nice helper because we can return an empty optional object if there is no match. Similar to the insert method, we provide a one-parameter version of the subtrie method, which automatically takes iterators from the input container. In the main function, that's already it. Let's put the new trie class to use in our main function by instantiating a trie specialized on string objects and fill it with some example content. Let's first print the whole trie. Then we obtain the subtrie for all the input sentences that start with hi and print it. Let's compile and execute the code. Go to the terminal and type in the command for compiling the code. After the successful compilation, let's execute it. Cool, this is the result. First it returns all the recorded sentences, and then it indeed returns us only the two sentences that start with hi when we query the trie for exactly that subtrie. Next we implement a search input suggestion generator with tries. Let's take a look at the code example. So go to the Atom editor, then click on the ex2 directory, and inside that, click on the wordsuggestion.cpp file. This is the entire code. Here, we will implement a terminal app which accepts some input and then tries to guess what the user might want to look for based on a cheap text file database. Let's understand the code. As always, includes come first, and we define that we use the standard namespace. We use the trie implementation. Let's add a little helper function that prints a line that prompts the user to enter some text. In the main function, we open a text file which acts as our sentence database db.text. We define that text file line by line and feed those lines into a trie. Now that we have constructed the trie from the content in the text file, we need to implement an interface for the user to query it. We prompt the user to enter some text and wait for a whole line of input. With that text input, we query the trie in order to get a subtrie from it. If we have such an input sequence in the text file already, then we can print how the input can be continued, just as in the search engine suggestion feature. Else, if we do not find a matching subtrie, we just tell the user no suggestions found. After that, we print the prompt text again and wait for the next line of user input. That's it. Before thinking about launching the program, we need to fill in some content into db.text, but I have already added this text file. Let me show you db.text file. As you can see, I have added all the content in the db.text file. The input can be really anything, and it does not even need to be sorted. Each line of text will be one trie sequence. So you already saw we have created the db.text file before we can run the program. Its content could look something like this. Now let's compile and execute the code. So go to the terminal and navigate to the ex2 directory. Next, we will clear the screen using the reset command. After that, type in the command for compiling the code. After the successful compilation, let's execute it. First it will ask, next input. Type in, what would? Suggestions are highlighted for you. Let's compare it with the db.text file. As you can see, after we type what would, it will give you suggestions based on what we have in our text file, like, what would aliens look like? What would MacGyver do? What would Bjorn Stroustrup do? And finally, what would Chuck Norris do? Now let's type another input. So we type in, why do? And suggestions are as highlighted here. Cool, we have successfully obtained the output. So here we have come to the end of this video. In the next video, we will be calculating error sum, implementing Mandelbrot renderer, and building split.